Hi, welcome to Element 14 Robotics 101 Part 4. This time we're gonna make a small mobile robot platform. Welcome to Part 4. In the previous parts we've covered everything from electronics, mechanics, to control algorithms and making a small robot arm. This time it's gonna be a small mobile robot. So what are mobile robots, how do they move, what are the different ways in they can move, or what's locomotion? That's what we're gonna find out first. Let's talk about locomotion. Locomotion is the ability of moving from one place to another. So in robotics, it's how does the robot move? There's not a set amount of types of locomotion because new robots are coming out each day. So for example, some popular categories would be a wheeled robot, like you would see for example on your robot vacuum cleaner, a bipedal robot, a robot that can walk, even a worm. You can imagine making a robot that mimics how a worm moves. And we're gonna focus on the wheeled robot since this is the category that we will be making. And of course they use wheels. But there is a bunch of different types of wheels and the ways they can use wheels. If we take a look at simple car and how a car steers, it steers by actually changing the angle of its front wheels when you turn the steering wheel, and that's how it actually steers, and all of the wheels are just pointing at the same point of the center of rotation for the curve. Another option would be differential or tank drive. In this case the wheels are fixed, we can just play with their speed and direction, and in the back we have a caster wheel or something like that. And so just by changing the speed of the wheels we can actually alter how the robot moves, whether it turns, whether it goes straight, and so on. And this is the type of robot that we're actually gonna make because it's the simplest of them all, since there is the minimal number of moving parts. Let's talk about the robot that we're gonna make, the differential drive robot. Where can you find them? Mostly on your floor, so something like this. The vacuum robot is the prime example of a differential drive robot. If we flip it around and see what's underneath, you can see that we have two drive wheels and one caster wheel. How it turns is, as I already explained, if you turn this wheel faster than this one, the robot will turn this way. You can also turn one in one direction, the other in the other direction, so you can move on the spot and so on, but we'll talk about more of that later. First thing that we're gonna do is gonna experiment with one of the motors that I'm gonna use that also has a built-in encoder and see what that's all about. Here is the key component for our robot, a small DF robot actuator, and here's why it's so good. First of all, we have the small electric motor which you can see here, then we have the gearbox, and here is the output shaft for the wheel, but also check this out. This here is an encoder. These two things here are small Hall effect sensors, and if we take a look with this magic little paper, you can see how this magnet actually looks like, with having a bunch of small magnets which can be with different polarities, which can be detected by these two Hall effect sensors, which are put here at 90 degrees, and you will see why rather soon. So we have two connectors here, one is for power to actually drive the motor, and the other one is for the encoder. So if we wire everything up and turn on the power supply, let's take a look at the scope. There is some signal issue, but here you can see a perfect square wave. Now, why do we have two of these? That's because from here we can only see whether we are spinning faster or slower. So if I lower the voltage, you can see the frequency go down, which means the motor is spinning slower, and if we increase the voltage, you can see that the frequency is picking up, meaning the motor is spinning quicker and quicker. Now if we turn on channel 2 as well, and let's just scale them to the same scale like so. If you take a look now, you can see it's the same frequency, but there is a phase shift between these two signals, and that's how we can tell actually in which direction the motor is spinning. So for example, if we look here, you can see the yellow signal or the first signal is rising first, but now if we go and switch over the power supply, reverse the polarity, you can see that actually the blue signal is now going first. And that's how we can tell the direction of spinning from these two. And we're just using one of them to actually tell the speed at which it is going. So yeah, that would be the motor. So let's go look at the rest of the electronics. Let's see what else we need besides those motors to make a complete robot. So first of all, we're gonna need the microcontroller, and I'm gonna go with the Raspberry Pi Pico W2. Why? Because it's a really cheap and rather powerful microcontroller, and it also has Wi-Fi and Bluetooth, so we can easily control it wirelessly. Besides that, we're gonna have 5 IR sensors that we will use as cliff detectors. Mostly the robots like the Roomba have the bump sensors, some even have LiDAR to detect walls. Just to make it simpler for testing, we will, instead of detecting walls, we will detect cliffs. So besides that, we have the motor driver that you can see here on the top. All it does is control the motors based on the inputs from the microcontroller. There are 2 signals per motor. One is the direction, so that's binary 1 or 0. And besides that, we have a PWM signal, which just tells the motor driver how fast to drive the motor. One thing to point is that these motors, or better said, the encoders on these motors are 5-volt logic, and our microcontroller here is 3.3-volt logic. So we also need a level translator like this. You can just use a small breakout board like this, or you can just use a voltage divider made out of resistors. But we need to step down that 5-volt logic to 3.3 volts. And to get that 3.3 volts, we're gonna have a battery pack that is at 6 volts for driving the motors, and a small linear dropout regulator to actually get our 3.3 volts for the microcontroller and all of the other logic stuff like the IR sensors and the encoders. So that would be it. The electronics are rather simple. Let's go and design a robot so we can finally test it. With the electronics done and motors tested, it's time to design a robot. So we're gonna jump into Fusion 360, do some CAD design around the motors, put the IR sensors, the microcontroller and everything else on, and see where that lands us before we can make it and finally program it and test it. And here is the design for a robot, and of course the whole design will be based around the motors that you've already seen on the bench. So literally I started just by placing these 2 motors at some distance and just trying to get them to align and to have some distance between here and here, so you can actually thread the cables without breaking them and things like that. And if we check the distance, this was around, so wait, let me do that again, from here to here. Yeah, that's around 126 millimeters. The wheels are thick 6 millimeters, so it will be 120 millimeters from wheel to wheel. Besides that, we have 5 IR sensors, so 3 here in the front, as you can see, and 2 in the back. Why we have 3 in the front is that we want to detect an obstacle coming directly at us, so when we face the cliff directly when we go to the front. And we also have the sensors on the side, so if we detect it if we come at it from a side and not just completely perpendicular. Besides that, we will have a perf board that will house all of the electronics that you've already seen, and in the back we have a battery pack. Besides that, here, and it's not modeled, I will just use a small caster wheel so that it acts like a support. So yeah, that's it when it comes to the whole design. One more thing to add about the wheels, I put this small notch here so that the Z seam from printing can go here, and I just place some regular O-rings over these wheels to act as tires. If you don't want to go that route, you can also just buy off-the-shelf wheels that I will include on the Element 14 community down below, that you can also find on Farnell. So let's take a look at this robot in real life. And our small robot is complete. I am really happy with how it turned out, especially with the small O-ring tires, which gives it a really nice grip on hard table surfaces. Everything is built around, of course, the 2 DF robot motors, and there are the 5 IR sensors that you can see, and the small caster wheel. The IR sensors, as you can see, when I put something in front of them, you can see them lighting up in green, and that's what happens when they're on a surface like this table, and when there's a cliff, they just don't detect anything. So it's working rather nicely. Here is the battery pack for powering everything. are electronics. The only thing left to do is program it and then test it, and hopefully it won't fall off at the table. The final thing that we need to do before testing is actually write the firmware and the code for the graphical user interface. And since it's 2026, I did this using Claude, so I'm just going to show you a few tips on how I actually did that. First of all of the things that you can see here it's a highly modular code and they were generated by Claude. One thing I tend to do is to go step by step when I'm actually using Claude for embedded projects, where it would essentially go the same way as if I was doing it myself, just starting off, for example, first with the motor driver, then the encoders, make sure that we get some readings, then compare that to the actual movements in real life, and so on. Just go step by step. Also, I like to keep two different threads. So we have the firmware thread and we also have the graphical user interface thread. You can optimize a lot of this. You can do all kind of skills and things like that. This is just a really simple setup, but it works rather nicely. One thing I always do is things like this. Since we have two pieces of software that need to communicate, so we have the firmware and the graphical user interface, I make sure that the session that's doing the firmware creates something that I'm calling the firmware API MD or a README file, and this is literally the documentation on how to actually communicate with the firmware. And like in the robotic arm project, this is just G-code style commands. But it literally gives it the whole recipe, the whole cookbook of how every command needs to be configured and so on. And then when I'm doing stuff in the graphical user interface thread, all I do is tell it to always look at this file because it has all of the latest updates, so it can know how to update itself further. Besides that, something I'm trying to do also is something I call the Quack MD, which is essentially just rubber ducking, where you would just take a third agent to see usually a different architecture, so you can double check that your agents are actually doing what they're supposed to do, bunch of unit testing and so on. But for a simple project like this really speeds it up a lot. So now, for example, if we run the graphical user interface, let me just get that going here. It's gonna be, let me just see the name of the file, it should be run GUI. And here it is. Here is the whole interface. So at the top right you can see a top-down view of a robot with the sensor, so it can blink what sensor is activated. You can see the wheels, which also will light up. You can connect to it either over Wi-Fi or using USB serial. There is this whole map that will get updated as the robot moves, as you will see in the testing further. There is also a tuning tab. You can see raw data. And here you can also send commands like it's a simple serial monitor. This is my favorite feature, honestly, by far, where it's essentially a Wi-Fi serial monitor to the robot, so you can command it and see what it's saying back and forth. There's also this planner that we're gonna talk about, and so on. So yeah, that's how I did the whole graphical user interface and firmware. As always, all of the codes and all of those MD files will be available on Element 14 community. So let's get to the fun part of testing this robot. The first test we're going to do is some PID tuning. If you've missed that part of the course, you can go back to part 2 of this course, where I went into a deep dive when it comes to PID controllers, what they are, how they work, and how do we tune them. Here you can see some examples here, but essentially, to get you back to speed if you haven't heard of them, PID controllers are what we use to actually keep constant speed or go to a certain position when it comes to motors. So for example, if we go here and say start a square wave, let me just stop that, you can see the reference here, which is just like a trapezoidal. Actually it's a square wave, but these are just two different time points, and you can see how fast our motor is trying to achieve that. It's actually holding the steady state rather nicely, but it's just a bit slow. So tuning this, tuning PIDs means actually going, and let's go read from robot, tuning these gains so that we get the robot response as close as possible to this reference. So for example, here we want to increase the proportional gain a bit. Let me just put this to 5 seconds and resume. So let's test that out a bit. For example, if we put 0.5, that's for example going to be a bit too much, but let's say apply changes and let's see what happens. Stop. Yeah, and the robot didn't even stop because it bugged out because of the high current. Let's power cycle it. But if you look at the graphs here, you can see how much it started to oscillate in both steady states. And that's the main reason why the robot actually crashed, because all of these are, just imagine a bunch of current spikes with the motors, and this is just running off of a few AA batteries, so they can't provide enough current fast enough. So let's reconnect to our robot and run this test again. Let me just reset some stuff. Enable, go to tuning, we're gonna click resume, read from robot, and let's actually update it a bit smarter and put, for example, a 5 here. We can click apply changes, and now if we click start square wave, you can see that it's still a bit unstable, but it's following the reference rather nicely. So we should probably tune it down a bit. Let's put, for example, 4 here. Click apply changes and let's try that. Let's click pause. Yeah, for this I will call this spot on. You can see how fast it responds, and it also follows the reference rather nicely. Maybe we can just go a tad lower, like so. Apply changes. Let's just do another test. Yeah, this is pretty nice, and this is what I am gonna keep, and I'm just gonna go save to flash. And that's how you can actually do PID tuning through this graphical user interface. So let's go and drive the robot around. The robot is now on the table and we can finally drive it around. So as you can see, we can do some simple turns, we can go forward, we can go backwards, and you can see all of the sensors light up. But if we try and run it to the edge, you will see the robot stops. There's a couple of ways we can implement this. One way is through the graphical user interface, but that can have some lag and the robot can fall over. Or if we do it directly in firmware, that's a much better and more stable option. So yeah, the robot is pretty easy to drive around. I'm just using my keyboard, and also you can see on the screen how the robot is tracking where it thinks it's actually going. But to be fair, there's of course gonna be some errors because we are only here calculating where it is based on the encoder positions. So it's not perfectly accurate, but it's better than nothing. So yeah, our little robot is doing great, and it won't let us just drive off the cliff. So the last thing we can do now is actually try and do an automatic mapping of this whole area and just let the robot run around. The little guy is driving around nicely, but let's do something more with it. Now it's just a small RC toy, but let's make it a bit autonomous. So my idea now is I want to put it on a raised surface. So imagine like a table but with nothing on it. So we can let it go and it can map out the whole area without actually falling off. So let's call that the mapper algorithm. I'm gonna draw a really simple algorithm where as we detect a certain edge, we're gonna go back, turn around, something similar that your robot vacuum would probably do. So let's draw that out, program the robot and see how it works. Time to talk about the mapping algorithm. First of all, let's take a look at the top view of the robot and the sensor position. So there are 5 sensors, but why? First of all, we have the 2 sensors in the front, right in front of the wheels, and that's to save the robot from falling off. They're also slightly outside both left and right, and that's because if it's going kind of parallel to the edge but still going towards it, there's a chance that if they're in line, that the wheel can still fall off if the detection is not that quick. So that's why they're a bit wider. In the back we also have 2 more sensors, same reason, just if you're going backwards just to detect that and not let the robot fall off. So there should be even more in the back to cover the coaster wheel, as well as you will also see later in the video. And in the front center we have another sensor, and that one is there so if we come right at the edge, We know that we hit it straight on if we trigger the center sensor first, and we can do a different kind of move, and you'll see why. Let's draw out how this would work. First of all, we have a flat raised surface, just imagine a table, and we will have a random starting position for a robot. All of our robot wants to do is just move forward, but as the sensors are triggered, it will do different things. So as it moves forward, the first trigger will be the front right sensor. Once we trigger that, the robot needs to go back and do a slight left turn, like this. And then it goes again. It will hit again, it will do the same thing. It will keep going on forward until it hits the center sensor like this. Once it does that, it's a completely new algorithm now. Now it moves back, does a 90-degree move to one side, does a short move towards the front, another 90-degree move, and then it just goes straight. This short move lets us actually do parallel tracks, so you can imagine how it can cover a whole rectangle. And now it will just go straight until it hits the other edge on the other side, and so on. So that's one simple algorithm that we will try and implement and see how it works in real life. Okay, so we've seen the mapper algorithm work on the paper, or in the drawing better said, but let's see how it works in real life. So I have the robot placed here on a raised surface, and the sensor will get triggered whenever it reaches any of the sides. So first of all, it should hit this side with the right sensor, it should do 2 jiggles and then hit that side, and we can monitor all of this through the graphical user interface. Let's just first set up how this should work. Let's put this at 80, for example. Stripes can be at 100 millimeters. Distance can be larger. Back off should be a bit bigger. And you'll see why. Let's put 70. And here maybe we can do something like 15. And these nudges 10, for example. Okay, so let's click start, and hopefully it won't fall off this time, as you will see in a clip probably later in the video. Okay. So you can see that it's detecting the front right sensor and it's doing that jiggle a few times. And now it should probably hit that side there. If it hits it straight up front, it should do a 180 turn, like so. And then it will come here and hit this side. And you can see all of that also in the graphical user interface. Yep, it hit it again. So it will move here again. This is the 100 millimeter move, so how far away one stripe is from each other. And you can see there is a bit of skew, and that's because these sensors are not ideal, since the wheels are slipping as the robot is moving around and so on. Ideally, we would have more sensors, for example, a LiDAR or something like that, to properly drive this robot and do sensor fusion, but that's a topic for another video. But yeah, as you can see, our little robot is exploring the whole table piece. It's not an optimal algorithm by any stretches of imagination, as you can see in the graphical user interface, but it's getting there. It will probably do a scan of the whole thing. So let's just let it run and do its thing. I will let it run as long as the battery allowed it, because as you can see it's forming a rather nice point cloud around the edges of the table, so we can actually see whether we can map out the whole bounding box. Thanks so much for watching the video and looking at me making this small little robot. Hope you're following along and you made something similar as well. This is the fourth part of this series and we will conclude it for now. If you however want me to continue and do any other robotics topics, please let me know, either down below on YouTube or on Element 14 community. I would love to explore more complex robotics projects with you. The idea with this was to keep it as simple as possible, so no any actual sensor fusion or anything like that, This was for people that were making their first robot and just wanted to see something move. And I mean, even here you can see stuff like this happen. And I didn't catch it in time, but yeah, it was a really fun series to do and a really fun project. Don't forget to subscribe to the channel, and all of the files, as always, are completely free on Element 14 community. So any questions, comments, suggestions, just leave them down below. See you next time.